Okay, let's get started. We are looking at the contour integral method for evaluating the inverse transform. We just got introduced to it, we saw what the formula was. Let's briefly recap the inversion integral. So, it is given by x of n is 1 over 2 pi j. It is a contour integral over C x of z times z to the n minus 1 dz, where C is a closed contour taken in the region of convergence. And this is evaluated using the Cauchy residue theorem. So, this is sum of the residues evaluated at the poles of x of z times z to the n minus 1 that are encircled by C. So, this is the residue formula, and if Z naught is a pole of order m, so this is of order m of x of z times z to the n minus 1. So, what we can do is we can explicitly factor that mth order pole outside. Therefore, x of z times z to the n minus 1 can be written as gamma z by z minus z naught to the m. So, all I have done here is I have taken x of z times z to the n minus 1 and explicitly factored out the mth order pole at z equal to z naught. The reason we want to do this is we need to evaluate the residues at every pole, and an mth order pole at z equal to z naught is the general case. And the residue for in this particular case is given by 1 by m minus 1 factorial d m minus 1 by dz to the m minus 1 of gamma z evaluated at z equal to z naught. So, as you have seen in the case of partial fraction expansion, if you have to calculate the residue at a pole, you need to cancel that pole out by multiplying by z minus z naught if z minus z naught were a simple pole, and then evaluate the rest of the expression at the location of the pole. So, this is exactly what we have done here. And As an example, we will take our good old friend 1 by 1 minus Az inverse mod z greater than mod A, and you know the answer is a to the n u of n. We will get the same answer using the contour integral. Therefore, let us now consider this. It is 1 by 2 pi j. So, x of z times z to the n minus 1. So, this is 1 by 1 minus Az inverse z to the n minus 1 dz, and this of course is 1 by 2 pi j. This is z by z minus a times z to the n minus 1. Therefore, this becomes z to the n. And if you look at the pole 0 plot, the circle that is drawn is mod z equal to mod a, and you have a pole at z equal to a, and for simplicity I have shown the pole to be real and positive, and there is an nth order trivial 0, and the region of convergence is outside this circle. Therefore, the contour C is a closed contour which is in this region, because the region of convergence is this. By definition, the closed contour C has to be taken in the region of convergence. Now, if you want to evaluate the contour integral, you need to evaluate the residues at the poles. There is only one pole here, namely at z equal to a. Therefore, all you need to do is you need to calculate the residue at the location of the pole. Therefore, residue at z equal to a is given by, you need to multiply by z minus a, so you cancel the pole. Therefore, this is z power n by z minus a, and then this needs to be evaluated at z equal to a, and you get back a of n, which is what you expect. So, we expected this to be the answer, and contour integral sure enough gives us this. So, are we done in terms of finding the inverse Z transform using the contour integral? Say that again. Okay, therefore, yeah, it has to be right sided, yes. So, can you develop on the answer and then complete it to point out what is left? So, what is it that we have assumed here? So, if you stop here, you are not done, because what we have assumed here is we have assumed n to be greater than or equal to 0, all right. So, this is the answer for n greater than or equal to 0, which is a to the n, which is along expected lines. What we have not yet shown is we have not shown that this gives you 0 for n less than 0, only then is this complete. Now, let us do that. We will point out that the above is true only for n greater than or equal to 0. Now, we will consider the case when n is less than 0. When n is less than 0, you can write this as 1 by z to the n by z minus a, where now n will be, we will consider values of n that are positive, because we have written it in this form. Okay. And now, this changes the pole 0 plot, whereas before you had only one pole, namely at z equal to a. So, that is still there, but what we now have is, we now have an nth order pole at 0. So, we have an nth order trivial pole. Okay. Therefore, if you now take this contour and look at it, it is now encircling not just the pole at z equal to a, but also the trivial nth order pole. So, when you compute the residue, you have to compute the residue at z equal to a and also at the nth order trivial pole. Okay. So, residue at z equal to a is easy, because you need to multiply by z minus a and then evaluate it at z equal to a, and you get 1 by a power n. Residue at z equal to 0, and now this is no longer a simple pole, it is a multiple pole. Therefore, now you have to apply the formula that was given. So, the formula that was given was 1 by n minus 1 factorial dn by d to the n minus 1 by dz to the n minus 1 of 1 by z to the minus a, and then you need to evaluate the n minus 1th order derivative at z equal to a. So, this will be, yeah, you are right, z equal to 0, because we are evaluating it at the origin, right. So, this is 1 by n minus 1 factorial, and now you need to find out the nth derivative of 1 by z minus a. So, this is nothing but minus 1 to the n minus 1 times n minus 1 factorial divided by z minus a power n evaluated at z equal to 0. So, this is from calculus, if you recall, this is the n minus 1th order derivative of 1 over z minus a, all right. So, nice cancellations are happening here. So, this cancels out, and then you need to evaluate this at z equal to 0. Therefore, you have minus 1 to the n minus 1 by minus a to the n. So, this is minus 1 to the n minus 1 by minus 1 to the n a to the n. So, which is minus 1 by a to the n, and sum of residues is 1 by a to the n plus minus of 1 by a to the n, and you get 0. So, now we have indeed shown the final answer is a to the n u of n. We saw it was a to the n for n greater than or equal to 0, and when n is less than 0, the contour integral gives us residues which add up to 0 for any negative value of n, and hence x of n is indeed a to the n u of n. For rational transfer function, yeah, question. Okay. So, if you look at, that's a good question. So, if you look at this circle, it is taken in the region of convergence, all right. So, when you have this picture for negative values of n, you see that it encircles this pole, the trivial pole, nth order trivial pole, and the pole at this one. Now, to see the difference, if you now take exactly the same x of z, but now you consider mod z less than mod a, and if you work the problem out, you will now take the contour C, which always has to be in the region of convergence. Therefore, this contour C will lie inside the circle mod z equal to mod a. And then you will see that in that case, it will not encircle the pole at z equal to a. So, it is a very simple exercise. In fact, 1 over a z inverse mod z less than mod a, you need to work it out using exactly this same method, contour integral, and then you need to show it is minus a to the n u of minus n minus 1. There you will see the difference contributed by the contour C lying inside the circle mod z equal to mod a, all right. Does that answer that question? Okay. So, we now have x of n to be indeed a to the n u of n. So, the contour integral, because of the Cauchy residue formula, that is given here, for rational functions, I mean, this is as easy to evaluate as anything else. Therefore, you are not really doing any contour integration, you are using the residue formula, and the residues are easy to find when x of z times z to the n minus 1 is rational. Now, what we will do is, we will show that the inversion integral is indeed correct in the sense that it gives you x of n back. So, this is what we want to prove. So, what we will do is we will start off with this. and then we will replace x of z by the z transform. So, this is nothing but 1 over 2 pi j integral over c. Now, instead of x of z, we will write this as k going from minus infinity to plus infinity, x of k z to the minus k times z to the n minus 1 dz. Note that here for the dummy index of summation, we have used k. You do not want to use n because n is already appearing here. So, that is why we used k. Now, we will happily interchange these two limiting processes, namely the integral and the infinite summation. Therefore, this becomes sum over all k x of k, and then this is 1 over 2 pi j, this contour integral z to the n minus 1 minus k dz. One over 2 pi j z to the n dz equals, I really can't, oh very good. So, this is 1 when n equals minus 1 and 0 otherwise, okay. I thought you people did not have a course on complex variables. Oh, okay. So, only some of you know this, all right. Therefore, using this result, if you apply this to this integral here, clearly the integral will be 1 if n minus 1 minus k equals minus 1. So, this implies this integral will exist only when k to n, otherwise the integral will be 0, and hence if you look at this expression here, for every value of k, it is going to be multiplied by a term that will be 0 whenever k is not equals n. Only when k equals n will this term be 1. For all other values, this term will be 0 and therefore, all these terms will vanish. Therefore, the only surviving term will correspond to k equal to n, and therefore, hence we get x of n as the final answer. Every other term in the summation is 0. Therefore, this indeed gives us x of n as expected. So, in the proof of the inversion integral, the key step is knowing this result, which follows from complex variable theory. When we did the Z transform properties, one of the properties was if you multiply in the time domain, you convolve in the other domain, except that in the Z transform case, the convolution in the other domain is complex convolution, and the Z transform of x of n times y of n was 1 over 2 pi j x of gamma y of z by gamma d gamma by gamma. This was the formula that was given, and it was mentioned at that point in time that this will make sense once we have the inversion integral formula with us. Now that we have the inversion integral formula with us, let us try to see if this is true. So, we are looking at the z transform of x of n times y of n. Therefore, we sum up over all n x of n times y of n, and then this is z to the minus n. This is after all the basic definition. So, this is sum over all n, and for x of n I will replace x of n by its inversion integral. Therefore, this is 1 over 2 pi j x of gamma to the n minus 1 d gamma. Again, you do not want to use z here because z already is part of the expression here. So, this is y of n times z to the minus n, and now we will do what we always do, we will interchange these two things. So, this is 1 by 2 pi j contour integral over C, and this is x of gamma to the now what is remaining is sum over all n y of n, and now we have z to the minus n gamma to the n minus 1. Therefore, this can be written as z by gamma to the minus n, all right. We still have to account for 1 power of gamma. So, now this can be written as d gamma by gamma, because you need gamma to the n minus 1. What falls out of this is gamma to the n. Therefore, this is this, and now you can immediately see that this is indeed 1 by 2 pi j x of gamma. This is nothing but y of z by gamma by definition, and this is d gamma by gamma. The only remaining thing that we have not yet shown is the ROC. So, I want you to take a stab at what the ROC should be. Remember, whenever you state the formula, you should not only state the algebraic expression, but also you need to give the corresponding ROC. And the hint is the ROC should be such that both x of gamma and y of z by gamma are part of the ROC. Z is a parameter here. Therefore, the multiplication in the time domain giving rise to this expression, now we have actually shown that it is indeed true once we have the inversion integral formula with us.